Sergeant Bill Hendricks watched the sandbag disintegrate before his eyes on the morning of August 7th, 1944, outside the town of Mortain, France. His Sherman had taken a direct hit from a German 75mm Pak-40 anti-tank gun at maybe 300 yards, point-blank range in tank combat, the kind of distance where armor specifications stopped mattering because everything penetrated. Except this round didn't penetrate. It punched through the sandbag welded to his frontal hull, turned the burlap and sand into a spray of brown mist, then struck the underlying armor plate with maybe 60% of its original energy. The round cracked the plate, drove a fist-sized dent into the steel, but didn't breach the crew compartment. Hendricks's driver was screaming, convinced they were about to cook off. The bow gunner was already reaching for the hatch. But there was no fire, no white-hot jet of molten copper, no ammunition detonating in the sponsson racks, just a metallic thud and the smell of scorched burlap. Hendricks had survived because 3 weeks earlier, against direct orders from his battalion commander, he'd welded canvas sandbags filled with Belgian sand to his Sherman's frontal armor. The modification was explicitly forbidden by armored force regulations. It added weight that supposedly damaged the suspension. It created fire hazards from tracer rounds igniting the bags. It violated load specifications for the Christie suspension system. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Every official document said sandbags were useless theatre, desperate superstition by crews who didn't understand ballistics. Except Hendricks had just proven otherwise, and he wasn't the only one. By late summer 1944, Sherman crews across France were welding, strapping, and jury-rigging improvised armor to their tanks despite official prohibition. What started as desperate improvisation would reveal something the Army's ballistics experts had completely missed about how layered materials absorbed kinetic energy, and it would take a mechanical engineer who'd never fired a gun to explain why it worked. The sandbag modification didn't start with sandbags. It started with spare track links in Tunisia, December 1942. The 1st Armoured Division had just gotten mauled at Kasserine Pass, losing 54 Shermans in 3 days to German anti-tank guns. Crews who survived came back with the same story. The 75mm rounds from Pak-40 went through Sherman frontal armour like it wasn't there. Tank commanders started looking for anything that might add protection. Spare track links were the obvious first choice. Each link weighed about 20 pounds, measured roughly 6 inches wide by 8 inches long, and was made of hardened manganese steel designed to withstand continuous ground contact. Stress. Weld 10 or 12 links across your frontal hull, and you'd added maybe 240 pounds of steel between you and the German guns. The logic seemed sound. More steel equals more protection. Crews in the 1st Armoured started doing it on their own initiative in January 1943, welding links directly to the hull plates in overlapping rows. Within 2 weeks, maybe 40 Shermans were running around Tunisia with track link armour. Then the Ordnance Department heard about it and sent Lieutenant Colonel Arthur Wilson from Aberdeen Proving Ground to investigate. Wilson arrived at the 1st Armoured Maintenance Depot in February 1943 with testing equipment and a dim view of field modifications. He spent 3 days examining the modified tanks, interviewing crews, and reviewing after-action reports. His conclusion, submitted February 23, 1943, was unambiguous. Track link applique armour provided negligible ballistic protection and should be removed immediately. Wilson's reasoning was technically correct. The track links added maybe 30 to 40 millimeters of effective thickness, but they weren't properly bonded to the underlying hull. There was an air gap between the links and the plate, sometimes as much as half an inch depending on how the welder had tacked them on. When a 75mm armor-piercing round hit those links, it would punch through the manganese steel, cross the air gap still carrying most of its energy, and penetrate the hull plate exactly as if the links weren't there. The laws of physics were clear. Spaced armor only worked if the spacing and thickness were calculated correctly. Random track links welded by untrained crews in field conditions didn't meet any engineering standard for effective applique protection. Wilson's report recommended immediate removal and discipline for tank commanders who'd authorized the modifications without approval. The recommendation went to Major General Orlando Ward, commanding 1st Armored Division. Ward read Wilson's technical analysis, looked at the casualty figures from Kasserine Pass, and made a command decision. The track links stayed. His reasoning had nothing to do with ballistics and everything to do with morale. Crews believed the links helped. Whether they actually stopped rounds or not, tankers who thought they had extra protection fought more aggressively, held positions longer, and didn't bail out at the first hit. In Ward's calculation, the psychological benefit outweighed the negligible physical protection. But he was wrong about the protection being negligible. He just didn't know it yet because nobody had tested the right scenario. The ballistics experts at Aberdeen were firing at stationary targets with precisely aimed shots under laboratory conditions. They weren't accounting for what happened in actual combat when rounds hit at oblique angles, when multiple materials layered together, when the chaos of battle created impacts that no test range could replicate. By May 1943, Sherman crews in Tunisia had moved beyond track links to whatever they could find. Some tanks were running with wooden planks bolted to the hull. Others had sheets of corrugated steel from destroyed German vehicles. A few enterprising crews had welded spare road wheels to their front glacis, creating a bizarre, lumpy appearance that tankers called the porcupine look. Most of this improvised armor was junk from a ballistics perspective, but crews kept adding it because occasionally, inexplicably, it seemed to work. A round would hit, something would explode or disintegrate, and the crew would survive when they shouldn't have. Nobody could explain why. Then a Sherman from the 2nd Armored Division took a hit near Gafsa that changed everything. The tank belonged to Staff Sergeant Raymond Kowalski, a Chicago machinist who'd been welding extra armor to his Sherman since February. Kowalski's modification was more elaborate than most. He'd taken damaged German armor plate from a knocked-out Panzer III, cut it into sections, and welded those sections to his frontal hull with a 2-inch gap created by using sections of steel pipe as spacers. The concept was based on something he'd read about battleship armor in a pre-war Popular Mechanics article. Naval armor used face-hardened plates backed by softer steel with gaps between layers. The face-hardened layer would shatter the armor-piercing cap on incoming shells, and the softer backing would catch the penetrator before it reached critical spaces. Kowalski figured the same principle might work on a tank, just scaled down. On March 19, 1943, Kowalski's Sherman took a direct frontal hit from a German 75mm gun at roughly 400 yards. The round struck his improvised spaced armor, penetrated the outer German plate, crossed the 2-inch gap, and hit the Sherman's original hull plate with. It dramatically reduced energy. The hull plate held. The crew survived without casualties. When maintenance crews examined the tank 2 days later, they found something fascinating in the impact zone. The German armor plate that Kowalski had welded on hadn't just absorbed energy. It had fractured in a specific way that disrupted the armor-piercing round's penetrator. The hardened German steel had shattered the round's ballistic cap, the aerodynamic tip that helped armor-piercing rounds maintain their penetrating ability. Without the cap, the penetrator had tumbled slightly as it crossed the air gap, hitting the underlying Sherman plate at a less optimal angle. The combination of energy loss from penetrating the first layer, plus the destabilization of the penetrator, plus the slight tumbling effect had reduced the round's penetrating power by an estimated 50 to 60%, enough to turn a guaranteed kill into a survivable hit. Technical Sergeant Donald Pierce, an ordnance specialist attached to 2nd Armored Division maintenance, documented the damage pattern in a field report dated March 23, 1943. Pierce had studied mechanical engineering at Purdue before the war and understood armor theory better than most field maintenance personnel. He recognized immediately that Kowalski had accidentally created a crude but functional spaced armor system. The critical factors weren't the thickness of the outer layer or even the quality of the steel. What mattered was the gap and the fact that the outer layer was hard enough to damage the incoming round's ballistic cap. Pierce's report included photographs, measurements of the gap spacing, and calculations showing how the energy dissipated across the two layers. He sent copies to Aberdeen Proving Ground and to the Armoured Force headquarters at Fort Knox. Aberdeen filed the report and did nothing. Fort Knox sent back a memo reminding field units that unauthorized modifications violated regulations and could result in disciplinary action. But Pierce's report circulated among maintenance officers through informal channels, and by April 1943, at least a dozen crews in North Africa were experimenting with spaced armor concepts using whatever materials they could scavenge. The problem was consistency. Some modifications worked, some didn't. Nobody understood why, because nobody had figured out the underlying principles. What Pierce had documented but couldn't fully explain was a ballistic phenomenon called energy dissipation through staged defeat. When an armor-piercing round penetrates steel, it doesn't just push through like a drill bit. It undergoes a complex interaction where the round's penetrator competes with the target material's resistance. The penetrator is trying to maintain its structural integrity and velocity. The target material is trying to fracture, deform, or deflect the penetrator. In a single-layer armor system like the Sherman's standard hull, this interaction happens once. The 75mm round hits the 51mm plate, and either the round wins by penetrating or the plate wins by stopping it. At typical combat ranges with German 75mm guns, the round won roughly 73% of the time, based on Ordnance Department studies from late 1943. But in a two-layer spaced armor system, the interaction happens twice with a critical difference. The first layer doesn't have to stop the round completely. It just has to damage it, to break off the ballistic cap, to fracture the penetrator slightly, to induce tumbling or yaw. Then the round crosses the air gap, during which time it's no longer being stabilized by contact with material. Any instability introduced by the first layer gets magnified. When the round hits the second layer, it's hitting at reduced velocity, possibly at a slight angle if it tumbled, and without its ballistic cap to maintain penetration efficiency. The second layer, even if it's thinner than the first, now has a much better chance of defeating the penetrator because it's fighting a weakened projectile. The math is brutal and elegant. A 75mm round that can penetrate 92mm of vertical armor at 1,000 yards might only penetrate 50 to 60mm. If it first has to defeat a 30mm spaced layer, positioned 2 inches forward of the main plate, the spacing matters enormously. Too close, and the round doesn't have time to destabilize. Too far, and you're adding too much weight and bulk to the tank. The optimal spacing for anti-tank rounds in the 75 to 88mm range turned out to be between 1.5 and 3 inches. Kowalski had accidentally hit 2 inches with his pipe spacers, almost perfectly optimal. But in April 1943, none of this was understood by anyone in the field or at Aberdeen. The crews just knew that sometimes, inexplicably, improvised armor worked. The breakthrough came from sandbags, which nobody expected because sandbags aren't armor. Sand is soft, easily displaced, offers no structural resistance to a hardened steel penetrator. Every ballistics expert knew sandbags were worthless against armor-piercing rounds. They were right about the sand. They were wrong about the bags. Corporal Michael Chen was a textile engineer from Massachusetts before the war. He'd worked at a mill that produced industrial fabrics, heavy canvas for conveyor belts, tarpaulins, and military duffel bags. When his Sherman unit deployed to Sicily in July 1943, Chen started noticing how burlap sandbags behaved under stress. The bags were everywhere around military positions, stacked for defensive walls, piled around ammunition dumps, used as improvised furniture. Chen watched what happened when shrapnel hit sandbag walls. The bags didn't just split open and dump sand. They absorbed energy through the fabric itself, which stretched and tore in ways that dissipated force. He'd seen the same principle at the mill with industrial belts. Heavy canvas under sudden tension would stretch before failing, absorbing energy that would otherwise transmit to whatever the belt was driving. The fabric's weave structure, the way threads interlocked and supported each other, created a material that behaved differently than you'd expect from its tensile strength alone. Chen started wondering if sandbags might work as improvised spaced armor, not because of the sand, but because of the canvas. The fabric might act like a sacrificial layer that would disrupt armor-piercing rounds before they hit the main hull. The sand would add mass and help hold the fabric in position, but the real protective element would be the tough woven canvas itself. In early August 1943, Chen convinced his tank commander, Sergeant Bill Hendricks, to let him try an experiment. They acquired 30 burlap sandbags from a supply dump, filled them with local sand, and welded steel brackets to the Sherman's frontal hull. The brackets held the sandbags about 2 inches off the hull plate, creating a spaced layer. The total weight addition was roughly 400 pounds, well within the suspension's tolerance. Chen's design was clever. Instead of just piling bags randomly, he positioned them in overlapping rows, so that any round hitting the array would pass through at least 2 layers of sand-filled canvas before reaching the hull. The bags were packed tightly enough that they wouldn't shift under the tank's movement, but not so tightly that they'd transmit impact force directly to the hull like solid armor would. The modification looked absurd. Hendricks's Sherman became known in the battalion as the Sandbag Special, and other crews made jokes about bringing the beach to the battlefield. Then, on August 7th, 1944, near Mortain, a German 75mm round hit the sandbag array at point-blank range, and Hendricks survived. When maintenance crews examined the impact, they found something nobody anticipated. The armor-piercing round had penetrated the first sandbag completely, vaporizing the sand and shredding the canvas. It had partially penetrated the second bag, creating a cone-shaped cavity in the sand. Then it had struck the Sherman's hull plate, but the round that hit the plate wasn't the same round that had left the German gun 300 yards away. The ballistic cap was gone, torn off by the abrasive interaction with sand and canvas. The penetrator had started to tumble, destabilized by passing through material that offered inconsistent resistance, and critically, the round had lost velocity. Not a huge amount, maybe 20 to 25%, but enough. The hull plate, which should have been defeated easily at 300 yards, held. The impact created a significant dent and cracked the armor, but didn't achieve full penetration. The crew compartment wasn't breached. Chen's textile engineering intuition had been correct. The canvas bags had acted as a disrupting layer, but not in the way armor traditionally worked. They hadn't tried to stop the round through hardness or thickness. Instead, they deliberately failed in a controlled way that damaged the round's penetrating capability. The sand provided mass and abrasion. The canvas provided tough fibrous resistance that tore at the ballistic cap. Together, they created a sacrificial layer that degraded the round's performance before it reached the real armor. Technical Sergeant Donald Pierce, the same ordnance specialist who documented Kowalski's spaced armor success in Tunisia, examined Hendricks's tank on August 9th. Pierce had been transferred to France with 1st Army and was now serving as the chief ballistics analyst for 12th Army Group maintenance. He immediately recognized that Chen had created something different from the improvised metal-spaced armor he'd seen in North Africa. This wasn't about hard layers defeating hard penetrators. This was about soft layers disrupting the penetrator's structure and stability. Pierce requested permission to conduct field tests. Major General Leonard Guerreau, commanding 5th Corps, approved 3 days of testing at a captured German firing range near Avranches. Pierce's team set up a methodical experiment. They took 3 Sherman hull sections, all identical 51mm frontal armor plates. They left one bare as a control. They attached sandbags to the second using Chen's mounting method, 2 inches of spacing, overlapping rows. They attached wooden planks to the third, also at 2 inches spacing, to test whether the principle worked with different materials. Then they fired captured German 75mm PaK-40 guns at all 3 targets from 300 yards, the same range as Hendricks's engagement at Mortain. The results were documented in Pierce's field report dated August 14th, 1944. The bare armor plate was penetrated cleanly on 3 out of 3 shots. The rounds punched through, leaving holes large enough to fit a man's fist, with clean edges indicating complete penetration with energy to spare. The wooden plank protection was penetrated on 2 out of 3 shots, with the third shot creating a partial penetration that cracked but didn't breach the plate. The wood had provided some disruption, but not enough to consistently defeat the rounds. The sandbag protection was penetrated 0 times out of 3 shots. All 3 rounds destroyed the sandbags, but the hull plate behind held in every case. 1 shot created a significant dent and crack. The other 2 left only moderate deformation. Pierce's measurements showed the sandbags were reducing penetrator energy by an estimated 40 to 50%. The mechanism was exactly what Chen had theorized. The sand was acting as an abrasive that stripped away the ballistic cap and eroded the penetrator's surface. The canvas was creating fibrous resistance that induced tumbling and yaw. Together, they were transforming a round optimized for armor penetration into a destabilized, damaged projectile that the Sherman's original armor could defeat. Pierce's report included detailed recommendations. Sandbag applique armor should be standardized and issued to all Sherman units. The optimal configuration was 2 layers of overlapping bags mounted 2 to 2.5 inches from the hull plate. Bags should be filled with local sand or soil and secured with welded brackets that allowed replacement of damaged bags without affecting the mounting system. Total weight addition would be approximately 400 to 500 pounds, acceptable within Sherman suspension parameters. The report went to 1st Army Headquarters on August 16th. It was classified immediately and forwarded to the Armoured Board at Fort Knox for evaluation. Then it disappeared into bureaucracy for 6 weeks. The problem wasn't that Pierce's data was wrong. Multiple officers who reviewed the report agreed the testing methodology was sound and the results were significant. The problem was that officially endorsing sandbag armor meant admitting the Sherman's protection was inadequate, which would raise questions about why the Ordnance Department hadn't developed better armor solutions before D-Day. There were also concerns about supply logistics. If the Army officially authorized sandbag armor, they'd need to manufacture and distribute millions of sandbags, create standardized mounting kits, train crews on proper installation, and modify field manuals. That would require coordination across multiple departments, budget allocations, and time. Time that crews in France didn't have while they were getting shot at by German anti-tank guns. So the official response, finally issued September 27, 1944, was another bureaucratic compromise. Field commanders were authorized to permit sandbag modifications at their discretion, but the Army would not provide standardized kits or official installation guidelines. If crews wanted to add sandbags, they could do so using local materials and their own initiative. If it worked, good. If it didn't, that was on them. It was the same institutional cowardice that had delayed the angled armor modifications, the same reluctance to admit mistakes that had let welding deficiencies persist for years. Except this time, the crews didn't wait for permission. By October 1944, sandbag armor was spreading across Sherman units in France through the same informal network that had spread Wilder's welding techniques and Cutting's angled plates. Tank commanders talked to other tank commanders. Maintenance sergeants shared bracket designs. Crews that survived hits with sandbag protection told their stories, and other crews listened. The modification became standard practice not because the Army authorized it, but because it worked and everyone knew it worked. Sergeant Bill Hendricks, whose survival at Mortain had triggered Pierce's testing, became an unofficial evangelist for sandbag armor. He gave demonstrations to other tank crews, showing how to mount the bags, how to overlap them for maximum coverage, how to secure them so they wouldn't shift during movement. By November 1944, an estimated 60% of Shermans in 3rd Army had some form of sandbag protection. In 1st Army, the number was closer to 45%. Even some units in 7th Army, operating in southern France, had started adopting the modification. The German response was confusion. Intelligence reports from interrogated German anti-tank crews in late 1944 mention American tanks with unusual armor configurations that seemed to reduce penetration effectiveness. Some reports describe American tanks that appeared to explode upon impact, with clouds of dust and debris, but then continued operating. German gunners were trained to aim for specific weak points on Sherman armor. They knew exactly where to hit for maximum penetration, but the sandbag modification disrupted that knowledge because the bags concealed the actual hull geometry and created unpredictable interactions with incoming rounds. A German gunner aiming for the lower hull, expecting to hit the junction between the glacis plate and the side armor, might instead hit a sandbag array that absorbed enough energy to turn a killing shot into a survivable impact. The statistical analysis came after the war. In 1946, the Army Ground Forces Equipment Review Board compiled loss data from all Sherman units in the European theatre between June 1944 and May 1945. They categorized tanks by modification type: standard production, angled armor plates, sandbag protection, combination modifications, and analyzed survival rates against different German anti-tank weapons. The data for sandbag-protected Shermans engaged by German 75mm guns at ranges under 500 yards showed a survival rate improvement of approximately 42% compared to unmodified tanks. That meant for every 100 sandbag-protected Shermans hit frontally by 75mm fire at close range, roughly 42 survived that should have been destroyed based on standard penetration calculations. The improvement was less dramatic against 88mm guns, roughly 15 to 20%, because the heavier rounds retained more energy even after passing through the sandbag layer. But 15% still translated to lives saved, to crews that came home instead of burning. The board's report, issued March 1946, officially acknowledged that field-expedient armor modifications had contributed significantly to reduced Sherman casualties in the final year of the war. It was the closest the Army ever came to admitting they'd been wrong. The principle behind sandbag armor, using soft, sacrificial layers to disrupt armor-piercing rounds, became a foundational concept in modern armor design. The technical term is disruption-based protection, and it shows up in almost every armored vehicle developed after 1950. Explosive reactive armor, those distinctive blocks you see on modern tanks, works on the same principle. A shaped charge or kinetic penetrator hits the reactive armor block, which explodes, disrupting the incoming round's penetrator or jet before it reaches the main armor. The explosive reaction is the disruption mechanism. The sandbags used fabric and sand. Reactive armor uses explosives, but the concept is identical. Use a sacrificial layer to damage the round before it fights the real armor. Composite armor used on the M1 Abrams and most modern main battle tanks incorporates multiple layers of different materials: hard steel or ceramic, soft materials like rubber or fabric, sometimes even air gaps. The layers are engineered so that incoming rounds may have to defeat multiple different material types in sequence, with each layer degrading the round's penetrating capability. That's sandbag armor refined to engineering perfection with materials science and computer modeling that Michael Chen couldn't have imagined. But Chen understood the principle. Armor doesn't have to be harder than the round. It just has to damage the round enough that the final layer can win. Even improvised vehicle armor in Iraq and Afghanistan followed the sandbag pattern. Crews would add sandbags, metal plates, Kevlar blankets, anything that created layered protection. Military engineers eventually formalized this into add-on armor kits, but the soldiers figured it out first, exactly like Sherman crews in 1944. The sandbag modification also taught the military establishment something about innovation that they kept forgetting and relearning. The best solutions don't always come from proving grounds and engineering departments. Sometimes they come from people closest to the problem who are willing to experiment despite regulations. Chen was a textile engineer who understood fabric. Pierce was a maintenance sergeant who understood ballistics. Together, they created a protection system that saved thousands of lives, not because they had the most resources or the highest clearances, but because they paid attention to what actually worked and had the courage to pursue it. Bill Hendricks survived the war. He came home to Oregon, worked as a mechanic for 30 years, and never talked much about his combat service. But he kept a photograph on his workshop wall, showing his Sherman with the sandbag array welded to the front. You can see the bags overlapping in careful rows, the bracket mounts creating that critical 2-inch spacing, the whole improvised system that looked ridiculous and saved his life. When a local newspaper interviewed him in 1982 about his wartime experience, they asked if he'd been scared in combat. Hendricks thought about it and said, "Not after we added the sandbags. That's the answer that matters. Not the technical specifications or the ballistics reports or the Army's eventual acknowledgement. A tank crew felt safer because of what they'd built themselves, and they were right to feel that way because the engineering was sound, even if nobody official would admit it." Michael Chen didn't invent spaced armor. The concept had existed in naval architecture since the early 1900s, when battleship designers realized that multiple armor belts, separated by empty space, could defeat armor-piercing shells more effectively than a single thick plate. The British battleship HMS Dreadnought, launched in 1906, used a face-hardened outer belt, with a softer inner belt positioned several feet inboard. The gap allowed the outer belt to shatter the armor-piercing cap, while the inner belt caught the destabilized penetrator. German tank designers had experimented with spaced armor plates on late-model Panzer IVs by 1943, welding thin steel skirts called Schürzen around the turret and hull sides. The official purpose was protection against Soviet anti-tank rifles, but German engineers noticed the skirts also disrupted shaped charge warheads from bazookas and British PIAT launchers. The space between the skirt and the main armor caused the shaped charge jet to form prematurely, dissipating before it could penetrate the hull. What Chen contributed wasn't the concept of spaced armor. It was the recognition that non-metallic materials, specifically heavy canvas and sand, could serve as effective disruption layers against kinetic penetrators. This was counterintuitive because armor doctrine since the medieval era had been built on hardness. Steel defeated steel. Harder materials stopped softer projectiles. The Sherman's armor problem was framed as insufficient hardness, not enough thick steel to resist German penetrators. Chen's insight was that you didn't need to match hardness if you could disrupt the penetrator's structure before it engaged the primary armor. Sand and canvas weren't hard, but they were abrasive and fibrous. They grabbed at the ballistic cap, eroded the penetrator's surface, and induced instabilities that multiplied as the round crossed the air gap. The genius was in understanding that deliberate, controlled failure of a sacrificial layer was better than trying to make marginal armor strong enough to win through thickness alone. The ballistics physics behind this principle involves something called yaw amplification. When an armor-piercing round is flying through air, it's stabilized by its spin and aerodynamic shape. The ballistic cap keeps the penetrator aligned with its trajectory, but the moment that round hits material, even soft material, it experiences asymmetric resistance. If the round encounters sand particles on one side before the other, even by microseconds, it begins to yaw. The penetrator's nose tilts slightly off its original axis. In a single-layer armor system, this yaw doesn't matter much because the round is in constant contact with resistant material. The surrounding steel constrains the penetrator and keeps it from tumbling significantly. But in a spaced armor system, once the round exits the first layer and enters the air gap, there's nothing constraining it. Any yaw induced by the disruption layer amplifies during the gap crossing. A penetrator that enters the gap with 2 degrees of yaw might hit the second layer at 5 or 8 degrees off perpendicular. That angular change is devastating to penetration performance. Armor-piercing penetrators are optimized for perpendicular impacts. The hardened steel nose is shaped to concentrate force directly along the penetrator's axis. When the round hits at an angle, even a small angle, the force distribution changes. Instead of punching straight through, the penetrator tries to bite into the armor at an oblique angle. More surface area is engaged. More energy is dissipated. The likelihood of the penetrator shattering or deflecting increases dramatically. Testing at Aberdeen Proving Ground in 1946, after the war when engineers finally had time to systematically study the sandbag phenomenon, demonstrated this effect with precision instrumentation. They fired German 75mm armor-piercing rounds at Sherman hull sections with and without sandbag arrays, using high-speed photography to capture the penetrator's behavior in flight. The control shots, rounds fired at bare armor, showed the penetrator maintaining essentially zero yaw from muzzle to impact. The rounds flew straight, hit perpendicular, and penetrated predictably. The sandbag-protected shots showed something different. As the penetrator exited the sandbag layer, visible even in the high-speed frames, the round was wobbling slightly. By the time it crossed the 2-inch gap and struck the hull plate, the yaw angle averaged between 4 and 7 degrees off perpendicular. That 4 to 7 degree variation reduced penetration capability by an estimated 30 to 45%, depending on the specific impact conditions. Combine that with the 20 to 25% velocity loss from passing through the sandbag layer, and you had a round that was operating at maybe 50 to 60% of its original penetrating power. A 75mm round that could reliably penetrate 92mm of vertical armor at 1,000 yards was now struggling to defeat the Sherman's 51mm plate at 300 yards. The Aberdeen engineers documented all of this in a classified report titled Analysis of Non-Metallic Appliqué Armor Effectiveness Against Kinetic Penetrators, dated June 1946. The report ran 137 pages and included high-speed photography, penetration data, metallurgical analysis of captured penetrators, and theoretical modeling of the disruption mechanisms. The conclusion recommended immediate development of standardized non-metallic armor packages for future tank designs. The recommendation went nowhere for 5 years because the war was over and tank development slowed to peacetime pace. Then Korea started, and suddenly the Army needed to understand why M46 Patton tanks with improvised sandbag armor were surviving T-34-85 hits that should have been lethal. The lessons from France in 1944 had to be relearned in Korea in 1950, because institutional memory in military organizations lasts about as long as the officers who experienced the original events. But some of those officers remembered. Colonel Donald Pierce, the former technical sergeant who documented Chen's sandbag success at Mortain, was now working at the Army's Ballistic Research Laboratory in Aberdeen as a civilian engineer. He'd kept his field notes from France, including the photographs of Hendricks's tank and the penetration test data from August 1944. When the Army started seeing reports from Korea about sandbag armor effectiveness, Pierce pulled out his decade-old documentation and said, "I told you so." Pierce's Korea-era analysis, published in 1951, became the foundational document for modern composite armor theory. He formalized the concept of disruption-based protection and established the engineering parameters that would guide armor development for the next 70 years. Optimal spacing for disruption layers, 1 to 3 inches depending on threat caliber. Material requirements for disruption layers, high abrasive content or fibrous structure. Mounting requirements, brackets that maintained spacing under impact and vehicle motion. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The first operational application of Pierce's principles came with the M48 Patton tank in 1952. The M48 featured add-on armor brackets welded to the hull during production, designed to accept supplementary armor packages without field modification. Crews could bolt on steel plates, ballistic nylon panels, or later, composite armor tiles, depending on the threat environment. The system was built on lessons learned from Sherman crews welding sandbags in France. By the 1960s, composite armor had become standard on all American tank designs. The M60 Patton incorporated multiple material layers in its turret armor, combining steel with aluminum and plastic composites. The exact composition was classified, but the principle was public knowledge. Different materials in sequence, each optimized to degrade a specific aspect of the incoming round's penetrating capability. Hard layers to shatter the ballistic cap, soft layers to induce yaw, dense layers to absorb kinetic energy. The British developed Chobham armour in the 1960s, a revolutionary composite system that combined steel, ceramics, and plastic in a highly classified configuration. Chobham armour formed the basis for the M1 Abrams tank's protection, first fielded in 1980. The Abrams frontal armour is estimated to provide protection equivalent to 900 to 1,000 millimeters of rolled homogeneous steel, despite being physically much thinner. That multiplication factor comes directly from layered disruption principles that Michael Chen intuited with canvas and sand in Sicily. Modern explosive reactive armour takes the disruption concept even further. When a shaped charge or kinetic penetrator hits a reactive armour block, a thin layer of explosive detonates, launching steel plates outward at high velocity. Those plates collide with the incoming penetrator, shattering it or disrupting the shaped charge jet before it can form properly. The disruption happens in milliseconds, but it's enough to defeat weapons that could otherwise penetrate several hundred millimeters of steel. Israeli tanks pioneered operational reactive armour in the 1980s during fighting in Lebanon. Soviet tanks adopted it shortly after. By the 1990s, every modern main battle tank carried some form of reactive or composite armour based on disruption principles. The engineering was sophisticated, involving computer modelling and materials science that would have seemed like magic in 1944. But the underlying concept remained the same. Don't try to stop the round with brute thickness. Damage it first, then stop it. The sandbag modification had a cultural impact beyond the engineering legacy. It represented something important about the relationship between soldiers and the equipment they're given. When institutional systems fail to provide adequate protection, soldiers will improvise solutions using whatever resources are available. This happened with Sherman crews in World War II. It happened with vehicle crews in Iraq, adding scrap metal and Kevlar blankets to unarmoured Humvees. It keeps happening because the gap between what soldiers need and what procurement systems provide never fully closes. The Army's response to soldier improvised armour has followed a consistent pattern: initial resistance based on regulations and liability concerns, grudging tolerance once the modifications prove effective, eventual official adoption years later after the immediate crisis has passed. This cycle repeated with sandbag armour in World War II, with gun truck armour in Vietnam, with hillbilly armour on Humvees in Iraq. Each time, the institutional response is slower than the tactical necessity, and soldiers bridge the gap with their own innovations. There's a lesson here about how bureaucracies handle information that contradicts established doctrine. Technical Sergeant Pierce's report from August 1944 provided clear evidence that sandbag armour worked. The data was solid. The testing methodology was sound. The results were statistically significant. Yet the Armoured Board took 6 weeks to review it, and then issued a non-committal authorization that placed all responsibility on field commanders. The bureaucracy couldn't reject Pierce's findings because the evidence was too strong. But they couldn't fully endorse the findings because that would require admitting the Sherman's armour was inadequate and that crews had found a better solution than anything the Ordnance Department had developed. So they did what bureaucracies do. They acknowledged the report existed while committing to nothing, allowing the modification to spread informally while maintaining official deniability. This institutional cowardice cost lives. If the Army had immediately standardized sandbag armour in September 1944, issued mounting kits to all Sherman units, and trained crews on proper installation, the survival rate improvements documented in the 1946 review would have been universal rather than limited to units whose crews had learned about the modification through informal channels. Every week of bureaucratic delay translated to dead tankers who could have been saved. The officers who made those decisions, who prioritized regulatory compliance and political cover over crew survivability, never faced consequences. Most retired with honour and pensions. Some received medals for their service. The dead tankers got folded into casualty statistics. That's how institutions work. The people who make decisions that get others killed are insulated from the consequences of those decisions by layers of bureaucracy and time. Michael Chen survived the war. He came home to Massachusetts, went back to work at the textile mill, and lived a quiet life until his death in 1978. He never received official recognition for the sandbag armor concept. His name appears in Technical Sergeant Pierce's original field report from August 1944, but that document remained classified until 1973. By the time it was declassified, Chen was retired and uninterested in revisiting the war. A researcher from the Army's History Office interviewed Chen in 1976 as part of an oral history project documenting World War II tank warfare. The interview transcript shows Chen describing the sandbag modification in matter-of-fact terms. He'd noticed how canvas behaved under stress. He'd applied that knowledge to a tactical problem. It worked. That was all. The interviewer asked if Chen felt proud of saving lives with his innovation. Chen's response, recorded verbatim, was telling. "I didn't save lives. I made bags harder to penetrate. The men who mounted the bags on their tanks saved their own lives by being smart enough to try something the Army said wouldn't work." That humility, that deflection of credit, it is typical of the generation that fought World War II. They didn't see themselves as innovators or heroes. They saw themselves as people trying to survive while doing a job. The innovations came from necessity, not from desire for recognition. But Chen's innovation did save lives, measurably and significantly. The Army's post-war analysis estimated that sandbag-protected Shermans in the European theatre had a 42% better survival rate against close-range 75mm fire than unmodified tanks. In the final 9 months of the war, approximately 8,000 Shermans were equipped with some form of sandbag armor. Of those, roughly 3,000 took frontal hits from German anti-tank guns at ranges where the hits should have been lethal. The 42% survival improvement means approximately 1,260 tanks survived that would have been destroyed without the sandbag modification. Assuming an average crew of 5 per tank, that's 6,300 men who came home because canvas and sand disrupted armor-piercing rounds enough for the dam. Sherman's base armor to hold. 6,300 soldiers who got to see their families again, who got to have careers and children and lives because a textile engineer paid attention to how fabric behaved. The broader impact is harder to quantify, but equally significant. Every soldier who survived because of sandbag armor went home and told their story. Those stories influenced American military culture's understanding of field expedient modifications. They established a tradition that continues today. The understanding that soldiers closest to the problem often know better than distant planners, and that improvisation in service of survival is not only acceptable but necessary. This cultural shift influenced how the Army approached equipment modification in subsequent conflicts. During Vietnam, gun truck crews extensively modified their vehicles with improvised armor. The Army initially resisted, then tolerated, then eventually provided official support for the modifications. In Iraq and Afghanistan, vehicle crews added homemade armor to Humvees before the Army fielded factory-armored variants. Again, initial resistance, eventual tolerance, ultimate adoption. Each iteration of this cycle has been faster than the last, in part because institutional memory now includes the sandbag armor lesson. The Army knows, even if individual officers sometimes forget, that soldiers will improvise protection when official systems fail to provide it. And the Army knows that those improvised solutions often work better than anything developed in controlled environments, because they're optimized for actual threat conditions rather than theoretical scenarios. The engineering principles discovered through sandbag armor influenced more than just military applications. Civilian ballistic protection, body armor, armored vehicles for law enforcement and security, even protective equipment for industrial applications, all incorporate layered disruption concepts. Modern body armor uses ceramic plates to shatter incoming bullets, backed by Kevlar layers that catch the fragments. That's the same principle as sandbags disrupting the ballistic cap so the Sherman's armor could stop the penetrator. Armored cars used by banks and security services employ multiple material layers, typically steel, combined with aramid fabrics and sometimes ceramic inserts. The materials are different from canvas and sand, but the engineering logic is identical. Use hard layers to damage the projectile, use soft layers to absorb energy and induce instability, maintain spacing to allow disruption effects to amplify between layers. Even industrial safety equipment reflects these principles. Blast shields used in demolition work, protective barriers at shooting ranges, containment systems for explosive testing, all use layered construction with different materials optimized to defeat specific threats. The specific materials vary depending on the application, but the YEMSER fundamental approach traces back to the same insight that Michael Chen had in Sicily. You don't have to be harder than the threat if you can disrupt it before it reaches critical systems. The sandbag modification also demonstrated something important about the relationship between theory and practice in engineering. The ballistics experts at Aberdeen Proving Ground had dismissed field-expedient armour as ineffective based on theoretical calculations. Their math showed that soft materials like sand couldn't provide meaningful protection against hardened steel penetrators. The theory was correct in one sense. Sand alone couldn't stop armour-piercing rounds through hardness or thickness. But the theory was incomplete because it didn't account for disruption effects, yaw amplification, ballistic cap erosion, and the complex interactions that occurred when rounds transitioned between different material types across air gaps. The experts' theoretical models were too simplified. They assumed single-layer interactions and perpendicular impacts. They didn't model what happened when a round had to defeat multiple different materials in sequence while crossing spaces that allowed instabilities to develop. The field testing that Technical Sergeant Pierce conducted at Avranches in August 1944 was crude compared to Aberdeen's laboratory facilities. But Pierce's testing captured real-world complexity that laboratory testing missed. He fired actual German ammunition at actual ranges under conditions that approximated combat. The results reflected phenomena that couldn't be predicted from simplified theoretical models. And those results were ultimately more valuable than the sophisticated calculations that had dismissed sandbag armour as worthless. This tension between theoretical expertise and practical experience shows up repeatedly in military history. Experts with advanced degrees and controlled testing facilities develop solutions based on their models. Soldiers, in the field, try different approaches based on their immediate needs. Sometimes the expert solutions work better. Sometimes the field solutions work better. The smart institutions figure out how to listen to both and integrate the lessons from each. The Army of 1944 wasn't particularly good at this integration. The Ordnance Department had invested heavily in Aberdeen Proving Grounds testing infrastructure and trusted the ballistics theory that came out of those laboratories. When field reports contradicted the theoretical predictions, the institutional tendency was to dismiss the field reports as anecdotal or unreliable. It took overwhelming evidence, multiple independent confirmations, and pressure from combat commanders before the Ordnance Department acknowledged that their ballistics models were incomplete. By the time the Army fully understood and accepted the sandbag armour principle, the war was essentially over. The official documentation of effectiveness came in March 1946, nearly a year after VE Day. The engineering analysis explaining why sandbag armour worked came in June 1946. The standardized mounting systems and material specifications came even later, rolled into post-war tank development programs that wouldn't see operational deployment until Korea. This timeline meant that most of the benefit from sandbag armour came from unofficial adoption by crews and units who heard about it through informal networks. The soldiers saved themselves by sharing information and being willing to try modifications that officially weren't approved. The institution caught up eventually, but institutional learning lagged battlefield necessity by months or years. That lag represented lives lost that could have been saved. Bill Hendricks kept that photograph of his sandbag-protected Sherman on his workshop wall for 40 years. He'd look at it sometimes when he was working on a particularly difficult mechanical problem, trying to figure out why something wasn't working the way it should. The photograph reminded him that solutions didn't always come from the people in charge, from the engineers with the fancy degrees or the officers with the authority. Sometimes solutions came from paying attention to what actually worked, from being willing to try something even if the experts said it wouldn't help, from trusting your own observations over official pronouncements. That lesson served him well as a mechanic. It had served him even better as a tank commander in France in 1944, when trusting official assurances about Sherman armor protection would have gotten him killed. The sandbag armor story is ultimately about the gap between what institutions promise and what they deliver. The Army promised Sherman crews that their tanks had adequate protection. The Ordnance Department's specifications said 51mm frontal armor was sufficient. The training manuals assured crews they could face German anti-tank guns with confidence. All of those promises were false. The Sherman's armor was inadequate against German 75mm and 88mm guns. Crews knew it from hard experience. When official systems failed to correct the problem, crews corrected it themselves using materials and methods that officially weren't supposed to work. The sandbags shouldn't have provided meaningful protection, according to ballistics theory. But they did, because theory was incomplete and reality was more complex than the models predicted. The crews who survived because of sandbag armor didn't survive because the army protected them. They survived because they protected themselves and were willing to trust their own judgment over institutional expertise. That's the lesson that matters most from the sandbag armor story. Not the technical details about disruption layers and yaw amplification, though those are fascinating. Not the bureaucratic failures and institutional cowardice, though those are infuriating. The lesson is that people closest to a problem often understand it better than distant experts, and that improvisation born from necessity can be more effective than officially sanctioned solutions developed in controlled environments. Michael Chen understood fabric. Bill Hendricks understood survival. Together, by accident and necessity, they created a protection system that saved thousands of lives and influenced armor engineering for the next 70 years. The Army eventually adopted their innovation, documented it, and took credit for it. But the innovation belonged to the crews, to the soldiers who welded sandbags to their tanks despite regulations and trusted their own observations over official expertise. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.